I will start from what was already mentioned here several times. So the unifying theme I am going to talk about starts from the analogy between the theory of number fields and function fields of curves. So the most basic example of the analogy originating from it is basically something that we can see as the arithmetic P1, and basically it will be exactly like shown on the picture. So we will just see the set of primes of the ring of integers as a sort of line with added point at infinity, and we will see it as a sort of P1 when this point at infinity suggests that it's exactly the compactification of our curve. And that analogy comes from Ostrowski theorem, which basically says that all absolute value functions that one can possibly define on Q, so the field of fractions of Z, are either p-adic norms or the Archimedean norms. So p-adic norms will be those that will be in one-to-one correspondence with our primes, and the Archimedean absolute value is something that corresponds to exactly this compactification to this point at infinity. And exactly by analogy, we treat spectra of number fields, so finite extensions of Q, as arithmetic curves. So we call them arithmetic curves. So the work of Iwasawa and Tate, which already happened some time ago, completed this analogy by finding an arithmetic analog of the Riemann-Roch theorem. Maybe that analogy was even like more broadly known, but what was significant about their work, that it was a completely global approach using Adels, and they covered at the same time geometric and arithmetic cases, which was quite significant and elegant. So it was a big breakthrough, a very beautiful unifying theme. And then there were very high hopes to very quickly generalize this approach to the higher dimensions. But it appeared to be more difficult than was initially expected. As you could see in the previous talk, Adels already in dimension 2, they are quite complicated. And for this beautiful unifying approach, we really need to consider not only algebraic properties of Adels, but also topology. So the power of this method exactly stays in considering those both structures simultaneously, which are comparable between each other. So basically in this talk, I am going to present a new unifying approach that will be analogous to Tate and Iwasawa's approach, and it will treat simultaneously geometric and arithmetic case, but in dimension 2. This is work in progress. It's with Paolo Dolce and with Ivan Fesenko. And before I start, just to kind of make ourselves more familiar with what we are going to talk about, or with possible difficulties, and also to kind of put another point on the topic of our conference, on the unifying themes. I just want to present this picture of arithmetic surface. So you've seen some like pictures of arithmetic surface in Paolo's talk. This is maybe a bit simplified one. So basically, an arithmetic surface could be understood just as the scheme part. So basically what we typically take is a model of a curve which basically means that fiber over each prime. Here I take spectrum of the rings of integers, but in generality, of course, we can take any number field. So a fiber of such a surface is just a reduction of our curve modulo that prime number. And then like the idea that originated from Arakelov, that suggested how intersection theory on this sort of surfaces should be done, suggested that it's not enough to consider that's just the scheme part of this picture, but one has to take our curve, tensor it by C, and then glue the Riemann surface that we obtain this way to our picture, exactly as we can see in front of ourselves. And what happens? So definitely we have much richer structure. We obtain much richer structure this way. But of course, it complicates things a lot. So we are not purely scheme theoretic anymore. We have some kind of artificially glued object, which is actually enriched with a lot of analytic structure. So it's completely different than the rest. And as well known for Arakelov geometry, it's actually that part at infinity that maybe for many people seems more natural because it's just Riemann surface, very classical object, that really makes it difficult to solve problems that can be translated into the language exactly of this surface. But at the same time, of course, we have this beauty. We have the unifying theme between what is discrete, which we can see as this kind of category theoretical algebraic side, and continuous, which is exactly this more analytical part, like link between what is algebraic and what is analytic. And it's been certainly shown that it's worth pursuing. For example, I don't know, by the proof of model conjecture that exactly originates from this sort of way of thinking. Okay, so to start my talk, I would like to present my plan. It's very complicated, as you can see. So it will be divided by two main parts. So the first part will be one-dimensional theory, and I will mostly refer to Tate. And it will be slightly rephrased in the language that will be very convenient for presentation of the second part, which will be the two-dimensional theory developed by the analogy of it. Okay, so basically, we start from taking a function. This will be an adelic function, and such a function we will just in general we can take them more general than here, but let's say that we'll be just considering a function for a fixed idel when the idel is an invertible element of the ring of adels. And basically, adelic function means that we have a function, like for each local place, we have a function that is defined on the local field of adels. And here, our definition is actually very concrete, so we don't really need the general definition of functions of adels. So for each local data, our f alpha b is just a translation of a very concrete function, which we will denote by f1. when f1 is a characteristic function of the ring of integers of the local field for the non-Archimedean place, and is a Gaussian function, especially adjusted Gaussian function for Archimedean places. And then something that may be pretty shocking for someone who never seen Tate's thesis, Riemann-Roch theorem in Tate's thesis looks exactly this way. So basically, we have two sums. So here xi runs over elements of our number field on both cases, and f of f here means Fourier transform of a function f. So our arguments, they are rescaled by a certain fixed idel. So in general, in Tate's thesis, f can be taken like more general, but for our purposes, we just need our previously defined f1 to be plugged in here. And this formula is very simple. So once in Tate's thesis, what's developed in Tate's thesis, it's actually harmonic analysis over number fields. So here, by Fourier transform, we actually mean certain global Fourier transform, which is a product of local Fourier transforms over each local fields of our number field. And also K is a discrete subset of our ring of Adel, so it makes sense to take these sums, and this formula here, as I written under, it's actually just a very straightforward consequence of this global analogy of Poisson summation formula for the Fourier transform on Adels. And why is it Riemann-Roch? So I will try to at least give some intuition how to see that it actually gives us Riemann-Roch theorem. So basically, each divisor in our case can be represented by Deidel. It's just like one-to-one correspondence between like the non-trivial coefficients of an idel and non-trivial coefficients of the divisor. And basically, one can see that the non-Archimedean, the characteristic functions, this translation of characteristic functions of f, they literally just keep track of the points of the spaces H0 to appropriate divisors of divisor, let's say the alpha in our case, and the alpha of kappa and inverse of alpha when kappa is the canonical divisor. And basically, in other words, it can be some that our integral over k, which is basically, as I said, discrete, so it tends exactly the form of this function. In the geometric case, just literally counts the points of global sections. In the arithmetic case, it looks a little bit differently. It gives us a certain measure on the realifications of these global sections. So that will basically be needed to calculate the volume of lattice that is needed for the definition of the Euler characteristics in the arithmetic case. And basically, relatively easily, like analyzing what those functions actually do and analyzing the coefficients that appear through Fourier transform in that formula, I can really see that one indeed obtains classical Riemann-Roch formula in the geometric case. which can be written rewritten exactly as this difference of Euler characteristics, which is will be more convenient for us to use also to pass to the arithmetic case. So basically, in the arithmetic case, the formula looked exactly the same, but just as I mentioned, I will have it explicitly written on some slide later, but I will already say it now that the Euler characteristics in the arithmetic case will be the volume of certain lattice that we obtain exactly from embedding our H0 in its realification. So we have to be able to measure that lattice. And then the degree on the right-hand side will be just the degree of like completed divisor, which are typically called Arakelov divisors, even though it's just the dimension 1. And here it may be something that is already less classical, even for people that did see Tate's thesis. But it's in fact just a simple reformulation of what is known from Tate's thesis. So basically, what we would like to be able to do is to integrate not only on Adels, but on certain special subquotients of Adels, and this is exactly what is happening in Tate's thesis. And those subquotients, they're important because they're exactly related to dualities that we would like to use to obtain our results. So basically, we define induced function so given an f alpha on Adels, we can define an induced f alpha and then Adels divided by k. So this second indices here, they will be appearing especially later. They just indicate on which space we would like to take the function that we are talking about. So now we will define our small h0 and small h1. So we actually don't even touch here the spaces, the cohomology spaces as they are. So it's in arithmetic case, it's very difficult to, it's very tricky to talk about cohomology spaces, but explicitly for Tate's thesis, we have what we have given the size of the cohomology spaces. And this is exactly what we define here. So when one thinks what is given in Tate's thesis, it basically makes sense to put such definitions as here. So H0 is as I said, is just the integral over k, which is discrete, and H1 is an integral on h over k, which is actually dual to k. I will state it explicitly when I talk about duality part, but it's exactly the point that a over k is isomorphic to the space of characters of k, and this is why using this duality we define H1 this way. And then we actually obtain really, really beautiful formula for the Euler characteristics. In this case, in any case, in one-dimensional case. So basically, it's a logarithm of an integral of a function f alpha associated to our divisor. So it's just an integral over full Adels. So it's pretty elegant. And in the geometric case, one just gets what one expects to get. So one just gets the alternating sum of dimensions of actual cohomology spaces. And in the arithmetic case, one still gets what one expects to get. So what classically is taken as the Euler characteristics in the arithmetic case, which is covolume of a lattice obtained from our H0 with certain measure, which exactly is given by our divisor classically, or in our case by the function that we've defined by the Gaussian function. And just to go back to what I already mentioned and just stress it more. So what is the crucial point of all that theory are all the dualities. So the advantage of the adelic ring is that we do take a very big complete object with some topology that's compatible with algebraic structure, and it gets a bit more complicated, but it's really, really a powerful tool. And because of this size, it really, really encodes within itself a lot of symmetries that are maybe not so visible, symmetries and dualities that maybe are not so visible outside that structure. So basically, as I already mentioned, the space of characters of a number field is isomorphic to the quotient of A divided by K. And basically, here I basically just write a formula which is a consequence of that. And so basically that the inverse Fourier transform of F associated to divisor kappa alpha inverse when kappa is a canonical divisor is equal to F alpha considered already as a function induced on this space A divided by K. And here we also have some normalizing term, which is just our choice of what we want our formulas to look like. So the second term, the inverse of Fourier transform of at zero of something, that's just a normalizing term. So basically here we already see like justification of our previous definition of Euler characteristics and cohomology groups. So we indeed get that the integral over K, which was sort of size of the cohomology. I mean, it's kind of like H0 size, small H0 is equal to certain H1 associated to alpha in this case. And this is nothing more but just says duality, which we basically see we obtain from all our analysis here. And that's probably about what I want to say about one-dimensional theory. And for two-dimensional theory, I will just quickly recall the definition. I will certainly not go into all the details that you've just seen during Paulo's talk. So basically, I will also avoid adding extra notation indicating if we deal with arithmetic or geometric adels. It should be still relatively easy to follow since the theory is supposed to be unifying. So we are trying to do the same thing in both cases. We just have to keep in mind that, in fact, in the arithmetic case, things are slightly more complicated. So just recall that our ring of Adels is a big object in dimension 2. It's a restricted direct product of some completed object associated to curves on our surface. And we do have its sub-object. I denote them by B and C, but Paulus denoted B was Paulus A01 and C Paulus A02. So basically those together with the function field that I will just denote as big K later, they are, but especially B and C, they are kind of in dimension to playing the part of what the number field as a subspace of Adels played in dimension 1. So they are very important, and they really play crucial roles in dualities of Adels, which, by the way, was already mentioned in Paulus' talk, and I will certainly recall it in due course. So again, just to settle notation, for a divisor, we define adelic subspace bounded by this divisor. And then for any adelic subspace by G of D would basically mean the intersection of that subspace with A of D. So basically in two-dimensional case, Idels will be just the invertible elements of what we defined as B, what we denoted as B. And we follow the notation from one-dimensional case. So basically, we again can use notation d alpha. We again can use A of d alpha. So basically, again, Idels, in this case, they correspond to divisors. And we define as A of d1, just A of 0. So basically, it means that all the coefficients in our Idel are trivial. And yeah, and a bit more of notation. So we will just need for the statement of certain result, just not to lie. We will need an object which we will denote as A prime. So this will be a subspace of A, which have zeros at the components of Archimedean fibers. So basically at the skin part, it will be just equal to normal Adels, and all its components at the non-Archimedean fibers will be equal to 0. So of course, this definition makes sense only in the arithmetic case. In the geometric case, A prime is just equal to A. And again, for like any subspace of A, we can define G prime as just intersection of G intersected with A prime. Maybe it seems to me that I just forgot to say, I will just go back. So here, just to stress and to recall, B is an object that's global, it's an object associated to curves inside Adels. And C is an object associated to points. So it originates, B originates from local fields associated to curves, and C from local objects associated to points. This is why it makes sense that when we deal with divisors later and define Idels, it's the B that we use. So actually, our approach, what's nice about our approach is that it is quite explicit. So basically, here we have, I just write a two-dimensional adelic complex, which allows us to calculate adelic cohomology. So in geometric case, it's been long known that the cohomology groups obtained from adelic complexes are equal isomorphic to Zariski cohomology spaces. The definition of the maps are quite natural. And then we need to define, to calculate for our purposes, cohomology spaces with respect to our adelic subspaces for our applications. And for that, we just noticed that we have the following quasi-isomorphism. So we can take another complex such that the maps between the complexes induce isomorphism between their cohomology groups. It can be checked that they are quasi-isomorphic. And from this, we can easily read, relatively easily read, the following expressions for our cohomology spaces. So H0 naturally is just K, so it's the function field of our surface, intersected with A of D. Our H1 has a bit more complicated formulation. It's B plus C intersected with A of D, and all that quotient by space B of D plus C of D. And H2, one can read is basically A divided by B plus C plus A of D. And yeah, as it was mentioned already in 2 previous talks, adels, 2-dimensional adels, they are too big to have standard integration on, even too big to have even more refined versions of integration defined. Just it's impossible to define any measure that keeps track of the subtle 2-dimensional structures within them. So if we wanted to induce any measure, we would automatically lose the structure that we actually need. So this is what was said, but then we still can integrate on some subquotients of A. And it will show up that actually for our purposes, this is quite sufficient. And we will be able to check that all the cohomology spaces are basically good enough for constructing a good measure. And now, with analogy with our 1-dimensional case, we are going to choose some characteristic functions whose integrals will again serve as building blocks for homology theory. So, okay, again, I just recall that we fix an idel. And again, for a fixed idel, we will be considering a function. So each local function will be going from this local object associated to a curve AY into R, and the definitions are perfectly analogous to the 1-dimensional case. So basically, f alpha is equal to the characteristic function to A0, to its translation by its divisor of A0, and A0 it can be seen as analogy of the rings of integers in 1-dimensional case. And then we have a certain analogy of the Gaussian function. So here formula looks quite the same, but instead of just having an idel in front of our argument uy, we will have some function. Here I don't define this function for simplicity. That will be replacing the norm of an idel in 1-dimensional case. So basically, I will not be writing now explicitly the definition of the function f alpha that we induce on subquotients of A. We just have to believe that by analogy with what we've seen in one-dimensional case, it's pretty natural. We can induce a function on subquotients. And what we are going to do, we are going to find a measure on those subspaces that will allow us to integrate those functions on our appropriate subquotients and give us results as the dualities that we need. Okay, so maybe I'm like repeating myself too much, but I will not probably be giving the proof, but eventually, I mean, as I mentioned, the subquotients needed for the description will be good enough, but nevertheless, we have to be aware that the situation is quite subtle. So we know that in the geometric case, like from just standard algebraic geometry, the cohomology spaces are finite as being of finite dimension over finite field. But in the arithmetic case, it's not true anymore. So basically, for example, H0 of an adelic complex AX of 0 is just equal to the ring of integer of number field of the base over which our arithmetic surface is defined. So for example, in the case of our picture we saw at the beginning, when the base was the simplest possible, that would be Z. So we see that in particular, it's not finite. But the situation is not quite as bad. So even in the arithmetic case, we are good, since we can prove, I will actually explain how to do that, that K is discrete inside A. It's one of the problems related to our previous paper that Paolo said we are working on. It's the fact that the function field is discrete inside the ring of Adels. And then A divided by B plus C, which will be actually dual of K, is compact as a dual to K, which is discrete. And then we have exactly this point when we need to use this prime notation. So for the description of H1, we will be needing the following spaces, and one can prove that they are compact. So it's B of D prime plus C of D prime quotient by B of D prime, and another one is the C of D quotient prime quotient by K of D prime. So here, basically, the first one, the K, will be used for our H0. A divided by B plus C will be used for H1, and the last one will be used for, the second one is used for H2, the last one is used for H1. So basically, now I'm just recalling what I wrote before, what we calculated from our adelic complex. We have the following formulas for our cohomology spaces, or for the scheme part of the cohomology spaces. And just for the purpose of H1, we really have to know that we have certain isomorphism. So basically, we had this explicit formula for H1, which is B plus C of D divided by B of D plus C of D, but it's isomorphic exactly to the quotient of those two spaces that we just mentioned on the previous slide were compact. And as a consequence, and by perfect analogy with one-dimensional case, we pose the following definition. So the small h0 of the alpha will be just, again, logarithm over k over the function field of our function f alpha. And h1 will be logarithm of integral of b plus c divided by b f alpha minus logarithm of integral over c quotient k of f alpha. So this, I will just go back. This here we just have to see that this quotient corresponds to this minus in our definition. We cannot always split the quotient spaces into the different, into the difference of integrals, but in this case we can do that. So this is well defined, and the small h2 of the alpha is just minus logarithm of integral of a over b plus c f alpha. So we can basically see that just I will just mention by duality later, H0 is actually automatically dual to H2. Okay, and then we are ready to calculate the formula for the Euler characteristics. So we just take the alternating sum of what we've just seen above, and we can then check that it simplifies to the following beautiful formulas. So Euler characteristics of d alpha is just logarithm over the space C of f alpha minus logarithm over this space integral over space A quotient bf alpha. So here I avoid notation. Of course, we have to take into account when we integrate over spaces the functions induced on that subspaces, but I just wrote it this way to make notation simpler. And it's also worth noting that if we assumed, as I said, that in some cases when it's well defined, we can split quotient into the difference of integrals over the spaces. So if we were able to do that here in this last formula, we would see that actually Euler characteristic is sort of alternating formula of integral over C, then minus integral over A and plus integral over B, which is pretty elegant. We can't do it because it's not well defined, but it can be somehow intuitively interpreted that way. And okay, just again, to summarize our definition, to justify our definitions more, I will just talk about duality in dimension 2. Paul already talked about it in more of the details. So basically, it was mentioned that using a fixed character of Adels, we will be able to actually use usual Fourier analysis on our spaces on which we can integrate. And also, even without that, independently of that theory, we already know that characters of K, they are isomorphic to the space A quotient B plus C. So it was the space over which we defined H2. So as I said, it's automatically, first of all, we knew that that was formula for H2, but it's also automatically self-dual in our theory. And also the fixed character gives us a pairing. It's a pairing that Paolo defined in his talk. And with respect to this pairing, we can define orthogonal complements of spaces. So basically, orthogonal complement of a space are those elements of Adels. I wrote him 0, but we are in S1, so we actually should have 1 instead of 0. So basically, the idea is that are those elements who have trivial pairing with any element of H. And it was already mentioned in Paolo's talk that in our joint paper, we proved the following, that both B and C are self-orthogonal. We also proved that the intersection of the two is our function field. And as Paolo mentioned, those are actually versions can be seen as strong versions of reciprocity laws on surfaces. So I said before that the object B is associated to curves, and on a surface we have a reciprocity law, which basically says that certain residue, like sum of certain residues that we have induced from our theory, from our pairing along a fixed curve is trivial, and the same we have. So basically, one reciprocity law, the one for curves, basically. So basically, there's one reciprocity law which tells about reciprocity law along fixed curve, points on fixed curve, and another reciprocity law which tells about curves passing through a fixed point of a surface. So that's the reciprocity law on C. And basically, when we translate the reciprocity law into our language, they're exactly equivalent to one, not to one inclusion of both of our equalities. So yeah. And as promised, I said that we are also proving that actually our function field K is discrete in the rings of Adels. And as a consequence, it's dual, which I mentioned is A divided by B plus C is compact. And in fact, it is enough to check that K intersected with A of D is discrete in A for every divisor D. But the group K intersected with A of D is a finitely generated OK module, because as I mentioned before, this is just from the theory of isomorphism between adelic and Zariski cohomology groups. We can deduce that it's indeed discrete. So yeah, so that was actually something that was definitely needed to be able to integrate. I already said about other properties, like when I was mentioning. So we already know that our spaces are either discrete or compact, at least those associated to cohomology spaces, and therefore we can move to the part related to dualities induced by our Fourier analysis. So basically, we again can just play with Fourier transform. And we have the following equality. So here again, kappa and alpha are Adels, like kappa is just the canonical, just associated to canonical divisor. And we can basically check that F alpha A divided by B plus C is equal to the following thing. It looks a bit complicated, but let's see for the next slide. So what we are going. So basically, we can also read that by definition, F alpha A divided by B plus C of 0 is 1, but we also can check that it's an inverse Fourier transform of F kappa alpha inverse at 0 and F of F alpha A divided by B plus C at 0. And we can explicitly write what they are. And of course, from the first equality here, we know they're inverse to each other. So we indeed, as I said, for free get that our cohomologies are dual to each other. And then I'm already not giving details, but actually, in some sense, it's even easier to obtain a duality for H1s, just using Plancherel's formula for compact and discrete H1. And we obtain the following formula, duality for H1s. And in particular, we obtain the following formula for the Euler characteristics. So again, everything works perfectly by analogy. And just related to the classical Euler characteristics, we can actually check that this way in the geometric case, we get the classical Euler characteristic modulo some constant. As it's written here, our measures are chosen to be normalized in the way that H1 of D1 is equal to H2 of D1 is equal to 0. And then we can basically see that our Hi of D alpha is equal to logarithm of the number of elements in the classical cohomology space of Ax of D, the geometric one, minus the log of the number of elements in the cohomology space associated to D1. And hence, also applying duality, we get the following formula for H0. And then a simple calculation already shows us that indeed we get the close relation with the standard Euler characteristics in the geometric case. So we can also check that if we define the following index using our Euler characteristic, it will actually coincide with the intersection pairing in the geometric case. And we will also easily obtain from our theory as a natural consequence the two-dimensional Riemann-Roch formula with like just slight modification. And yeah, so the point of the theory is just that once we deal with the very subtle objects that are those subquotient spaces and analyze their topological and algebraic properties, we can really apply this this theory that is totally analogical to one-dimensional theory. And once we already check we have a good measure, things become pretty straightforward. But at the same time, things of course complicate in the arithmetic case. So we do have our theory working for the arithmetic case, but what we ideally would like it to be like, possibly, or we would at least like to know its relation, would like to know the relation of what we get in the arithmetic case with the Arakelov geometry, for example, and with the metrics we obtain using our functions with so-called Falting's metric on determinant of cohomology for anyone that knows Arakelov geometry. So if there is any close relation between those two, that would be actually really phenomenal, because that would be a really long missing global approach to Arakelov geometry. That is a lot to hope for, but that would be really beautiful. So this is something that we still haven't checked for the moment, and we still, of course, like we haven't checked if we get Arakelov intersection pairing exactly following the analogical formula. So this is something that is still out there to be finished. So yeah, I am a bit before the time, I suppose, but I hope that no one minds. Maybe we will have time for questions if someone has any for this one single time. So thank you again for your attention, and I hope that you enjoyed the talk.